Hello, we are team number 1, my partner Sophia and I, Chris. We are going to present the delivery number 5 of our statistical project about the water quality in Mexico. The content that what we're going to be talking about during the presentation is the following. First, we're going to give a summary from point 1 to 9 about the previous deliveries, including our finalized decision about the 3 scientific hypotheses and their corresponding statistical hypotheses. Also, we're going to talk about the simulation for selecting the distribution of our main variables and the exact parameters that need to be estimated in each hypothesis. Then, we are going to present the procedure we follow for all hypotheses to obtain the prior and posterior hyperparameter. After, we'll see the plots of the prior, posterior, and the distribution of the observed data and the decision about the hypothesis. Finally, we will talk about the comparison of the Bayesian and Fisherian results related to rejecting or not rejecting the hypothesis. CONAGUA is the National Water Commission, and it is an administrative body in charge of managing, regulating, controlling, and protecting national waters in Mexico. In 2019, CONAGUA established 2,764 water quality monitoring sites throughout the country. The main purpose of this study was to make a proper analysis of the status of the water quality in each state of Mexico. The contribution of this project is to demonstrate the status of the Mexican state with the worst perceived water quality, that is Tabasco.
Now we're gonna discuss the variables that we talked about in the last delivery. First, we have the biochemical oxygen demand at 5 days, which is measured in milligrams per liter. And then we have the chemical oxygen demand, which is measured at milligrams per liter. Then the total suspended solids, which is measured also at milligrams per liter. Now we have fecal coliforms. Fecal coliforms is measured in the most probable number in 100 milliliters. This is one type of coliform bacteria that is found mainly in animal digestive tracts and feces. Fecal coliforms are a more specific indicator of fecal contamination of water. Then we have E. coli. E. coli is a species of fecal coliform bacteria, and it is also measured in the most probable number in 100 milliliters. E. coli almost always comes from animal feces, and it is considered to be the best indicator of fecal water contamination. If E. coli is present, harmful bacteria or other pathogens may also be present. Now, a quick review of the type of variables. As we can see, there are 5 variables being tested, and all of them are continuous. The degree of interaction between variables is shown in the following table. All of this information was obtained by plotting the correlation tables between them and the correlation plots. The first relationship we can see is the fecal coliforms and E. coli, which have a highly or strongly correlated relationship with an R of 0.97. Then we have the E. coli and biochemical oxygen demand, which has a strong positive linear relationship with an R of 0.91. And then we have fecal coliforms and biochemical oxygen demand, which has also a strong positive linear relationship with an R of 0.91. Then we have the fecal coliforms and oxygen saturation, which has a weak negative linear relationship with an R of minus 0.22. And E. coli and oxygen saturation, which have a weak negative linear relationship with an R of minus 0.21.
In order to find the state with the worst water quality of Mexico, we already said that Tabasco has the lowest quality. CONAGUA in 2018 stated a distribution of the monitoring sites in superficial bodies of water divided by hydro-administrative regions, and there are 13 regions in Mexico: Peninsula de Baja California, Northwest, North Pacific, Balsas, South Pacific, Rio Bravo, North Central Basins, Lerma, Santiago Pacific, North Gulf,
Central Gulf, southern border, Yucatan Peninsula, and waters of the Valley of Mexico. Conagua estimated that 70% of the bodies of waters, rivers, lakes, lagoons in Mexico are contaminated. We chose to study the southern border of Mexico because according to a 2017 report by the National Water Commission, they stated that the most polluted river in Mexico is the Grijalva. The Tabasco territory is administratively part of the Grijalvo-Sumacinta River Basin. Tabasco is one of the states which make up the southern border region of Mexico. We are going to focus into the physical-chemical quality of the water of the rivers of Tabasco.
Conagua has a criteria for the monitoring sites that indicates the quality of the water following a superficial scale with different parameters regarding each variable separately. There are 5 different levels of the superficial scale. First we have excellent, then satisfactory, then acceptable, then contaminated, and finally strongly contaminated. These are the superficial scale for the 5 variables we're going to study. For example, in the biochemical oxygen demand of 5 days, when we have less than or equal to 3, we have an excellent quality of water. When it's between 3 and 6, we have a satisfactory quality of water. When we have between 6 and 30, we have an acceptable quality of water. When it's between 30 and 120, we have a contaminated water. When it's greater than 120 milligrams per liter, we have a strongly contaminated water. For the other 4 variables, the scale behaves the same only with their respective values and units. As we want to see if the water quality of Tabasco is bad, we are going to focus in the last 3 superficial scale: satisfactory, contaminated, and strongly contaminated.
Now we're going to talk about the scientific and statistical hypotheses. So first we have the scientific hypothesis, which is if the superficial water has a low content of suspended solids in natural conditions and a low content of organic biodegradable matter, then the water quality of its rivers is considered a good water quality. For this scientific hypothesis, we have 2 statistical hypotheses. The first one states that the mean of a biochemical oxygen demand during 5 days from the superficial water network of Tabasco is less than or equal to 6 milligrams per liter. So this is what the null hypothesis states: mean less than equal to 6, and the alternative hypothesis states that the mean is greater than 6. The second statistical hypothesis states that the mean of total suspended solids from the superficial network of Tabasco is less than or equal to 75 milligrams per liter. The null hypothesis states that the mean is less than equal to 75, and the alternative hypothesis states that the mean is greater than 75. For the second scientific hypothesis, we have if the superficial water has bacteriological contamination and residual water discharge, then the water quality of its rivers is considered a low quality. The first statistical hypothesis for the scientific hypothesis states that the mean of Escherichia coli, or E. coli, from the superficial water network of Tabasco is less than 850 most probable number in 100 milliliters of E. coli. So the null hypothesis states that the mean is less than or equal to 150, and the alternative hypothesis states that the mean is greater than 850. The second statistical hypothesis states that the mean of chemical oxygen demand from the superficial network of Tabasco is less than or equal to 40 milligrams per liter. The alternative hypothesis states that the mean is less than or equal to 40, and the alternative hypothesis states that the mean is greater than 40. For the third scientific hypothesis, we have the superficial water has a satisfactory quality for aquatic life and recreational use, with primary contact and other uses when there is low indications of bacteriological alteration of the quality. The statistical hypothesis for this scientific hypothesis states that the mean of fecal coliforms from the superficial water network of Tabasco is less than or equal to 1,000 most probable number in 100 milliliters. The null hypothesis states that the mean is less than or equal to 1,000, and the alternative hypothesis states that the mean is greater than 1,000.
To choose the distribution of each variable, we follow this methodology. This was used for all the 5 variables. First, we're gonna have the outliers detection using a box plot. Second, we verify the transformation with the probability density function plot, QQ plot, and PP plot. Third, we choose a distribution with the goodness of fit. Fourth, transform the data with the relation among the distribution table, if it's necessary, using the distribution previously chosen. And 5, choose a new distribution with goodness of fit with the transformed data.
After we did the goodness of fit and the necessary transformation, we obtained that the 5 variables follow a log normal distribution.
With the goodness of fit, we saw that all of our variables and their data follow a log normal distribution. However, to confirm this, we did a simulation for each variable, a sampling with replacement. With the goodness of fit, we chose the best 3 fit distributions for the variables, the ones that had the highest MLE. And using R, we made 1,000 samplings using those 3 distributions. And in each simulation of the 1,000, we ran a goodness of fit test, and we saved the distribution with the highest log likelihood estimator as the final distribution. At the end of the last simulation, we obtained the frequency of each distribution, that is, the times that each distribution was obtained, and we chose the distribution with the highest of the frequencies. In this case, it was the log normal. This table shows the simulation results for each of the variables. As I said before, each variable was simulated 1,000 times, and we can see that in all of the variables, the ones with the highest frequency are the log normal distribution. So this states that all of the variables follow a log normal distribution. And finally, we have the parameters of the distribution. These parameters are part of the log normal distribution. The log normal distribution is a versatile and continuous distribution. So the first parameter is the scale, and the scale parameter is the mean of the normally distributed natural logarithm of the data. Its range goes from negative infinity to positive infinity, and it can be found in the data with this equation. Then we have the shape parameter, which is always positive, and it is the standard deviation of the normally distributed natural logarithm of the data. The shape parameter is determined using this equation. And finally, we have the expected value that in this distribution is the mean, and it can be computed with this formula. Now for the prior and posterior hyperparameters. All the variables being analyzed are part of the exponential family, so this procedure is for all 5 variables. To obtain the prior and posterior hyperparameters for the Bayesian analysis, the first step taken was to make sure that the distribution chosen for each variable was the log normal distribution. Afterwards, the second step taken was to exponentiate the transformed data and run 1,000 simulations fitting the data to a normal distribution to obtain the log likelihood vector and the vectors of the parameters of the distribution. Following the simulations, the variance of the parameters was obtained in the fit and was compared to make sure that the variance was the known parameter. Once the variance was compared, the vectors of the parameters were used to obtain the prior hyperparameters with the fit distort function, fitting the vectors to a normal distribution. With the prior hyperparameters, using the equation for a normal distribution with a known variance, the posterior hyperparameters were calculated. After the prior and posterior hyperparameters were computed, they were used to plot a normal curve for each parameter to analyze the hypothesis. For the simulation to estimate the parameters of the likelihood function, after doing the goodness of fit test, it is known that all of the variables follow a log normal distribution and belong to the exponential family, as mentioned before. For the log normal distribution, the data is transformed using a logarithm. To obtain the vectors of the parameters for the log normal, it is required to obtain these vectors using the normal distribution in the simulation with the transformed data exponentiated. Once the data is exponentiated, the simulation takes place in a loop for bootstrapping. Sampling was used for 1,000 simulations to obtain the vectors of the parameters of the distribution, in this case, mean and standard deviation. Afterwards, when the loop ended and the 1,000 simulations were done, the vectors were saved as the values of the parameters for all the simulations. The vectors were then called and the NAs were taken out of the vectors so they could be fitted and analyzed. Now, when comparing the variance, after the vectors of the parameter were obtained, it was important to know which parameter played the role of a variable. To do that, the variance of each parameter was compared to see which of the parameters was known. As it can be seen, the variance of the sigma for the 5 variables is small. As variance of the 1000 sigma I is lower than the 1000 mu I, the parameter known and fixed is sigma. Now to obtain the prior hyperparameters. As mentioned before, the simulation was done through bootstrapping. Basically, the simulation consisted of a loop where vectors of both parameters during the loop were saved for the 1000 simulation. Once both vectors were called and the NA values were erased, both vectors were fitted with the fit-distur function using the normal distribution. This function obtains a compilation of data which holds the estimate values of the mean prior, mu0, and the variance prior, sigma squared 0, the hyperparameters. As you can see, these are the prior hyperparameters for all of the 5 variables.
Since the prior parameters represent the different scenarios of what is originally believed before introducing evidence to the analysis, the posterior parameters take into account the prior parameters and the evidence of the real scenario, hinting to the truth of the data. The posterior hyperparameters were obtained by using the prior hyperparameters, the known parameter, that in this case is the variance of the original data, the number of samples, that is n, of the original data, and the original data with the following equations. The one in the left to obtain the mean posterior hyperparameter, and this one to obtain the variance posterior hyperparameter. To be able to analyze the hypothesis, the normal curve of the prior, posterior, and the distribution parameters had to be plotted in order to observe if the null hypothesis will be rejected or not. To plot these curves, and because they follow a normal distribution, the mean parameters were used as the expected value, and the variance parameters were square-rooted and used as the standard deviation. Which means it was used the prior parameters to plot the prior curve, the posterior hyperparameters to plot the posterior curve, and since the prior and posterior hyperparameters follow a normal distribution, they were directly plotted. The parameters obtained for the original data to plot the distribution of the data were obtained with the maximum likelihood estimator previously. For DB05, when plotting the 3 curves together, it can be observed that the prior curve, the red one, is not shown properly mainly because the standard deviation of the prior curve is significantly larger than the ones in the posterior and normal curves, which then shows the prior curve to be spread in the plot differently than the posterior and normal curves. With regards to the posterior and the distribution of the data curve of DB05, it can be observed that even though they show different means, the standard deviation of both curves are also very similar. This can be explained by the fact that the variation is more robust and takes into account more information and can be more accurate. As it can be seen, the pink line is a graphical representation of the threshold to see if it's before, after, or over the curve in order to determine if the null hypothesis is rejected or not rejected. The line graphically is just there in representative and visual way. However, the equality of the threshold is the accurate value and the one that will determine the outcome of the rejection. This is the prior normal curve of DB05, and its null hypothesis is rejected because it states that the mean is lower or equal to 6, and the threshold is on the left side of the normal curve, which means that the null hypothesis is rejected for the prior distribution. For the posterior and Fisherian curve, as said before, they have similar behaviors, and for the variable DB05, since the mean is lower or equal to 6 and the threshold is on the left side of the normal curve, the null hypothesis is rejected for both of them. For DQO, it can be seen that the prior, the posterior, and the Fisherian curve have the same behavior as the DB05 plots described before. Following the same threshold criteria, the null hypothesis of the prior distribution is rejected, and for the posterior and the Fisherian curves, the null hypotheses are not rejected. For the SST variable, the plots follow the same behavior as DB05 and DQO plots. However, the threshold criteria only follows the behavior of the DQO variable. The null hypothesis of the prior distribution is rejected, and for the posterior and the Fisherian curves, the null hypotheses are not rejected. In FC's curves, besides the height difference of the posterior and Fisherian curves, both are accurate analyses of the data because even though they take different approaches, their standard deviation behaves similarly. Following the same threshold criteria, the null hypotheses of the three distribution are rejected. For the Ecoli curves, here it can be seen that they behave the same as fecal coliform curves, and following the same threshold criteria, the null hypotheses of the three distribution are also rejected. By comparing the result of the Fisherian approach with Bayesian approach, we can see that in DB05, fecal coliforms, and E. coli, the three distribution have the same results. The three rejected the null hypothesis. However, in the case for DQO and SST, only the posterior and the data distribution had the same results. Both did not reject the null hypothesis. The prior distribution takes only into account subjective beliefs about the parameters, while the posterior distribution represents different scenarios and the updated evidence with the original data. In general, we will not reject the result obtained in the posterior distribution, since Fisherian approach only looks at the evidence of the data and doesn't take into account possible scenarios that could happen. While Bayesian in the posterior, they use the prior and the evidence, thus provides a broader picture. Doing the analysis by Bayesian approach, we will stay with the result of the posterior distribution regarding whether a hypothesis is reject or not reject. That in this case was always the same for the Fisherian results. This is all for today. Thank you very much for your attention.
Now we have fecal coliforms. Fecal coliforms is measured in the most probable number in 100 milliliters. This is one type of coliform bacteria that is found mainly in animal digestive tracts and feces. Fecal coliforms are a more specific indicator of fecal contamination of water. Then we have E. coli. E. coli is a species of fecal coliform bacteria, and it is also measured in the most probable number in 100 milliliters. E. coli almost always comes from animal feces, and it is considered to be the best indicator of fecal water contamination. If E. coli is present, harmful bacteria or other pathogens may also be present. Now, a quick review of the type of variables as we